Hello, this is Dr. Maria Weber, and this is your mini lecture about resistance. So behind me, I have a bunch of really pretty resistors. Remember that our resistors, we can tell what their resistance is based on the color coding bands on their sides, which we've seen in lab before. So let's start first by talking about Ohm's law, which is going to turn out to be a really powerful thing for us. And so we know that the current is proportional to the voltage in our system. And the resistance is defined as being equal to this voltage or potential difference divided by the current. Now, this resistance is measured in units of ohms, represented by a capital Greek letter omega. 1 ohm is equal to 1 volt per ampere. Now, for many materials, resistance remains constant over a wide range of voltages and currents. These materials we call ohmic materials. And with that in mind, we have a relationship called Ohm's law, which is that the voltage is equal to the current times the resistance. And you can also rearrange that to say that the current is equal to the voltage over the resistance. So here we have a schematic of a current. We've got our battery here, or our power source, supplying us with a potential difference. Our current is running from the positive terminal to the negative terminal. It's moving through this resistor. And we can say that the current here is going to be equal to the potential difference, or the voltage from our power source, divided by the resistance of our resistor. Now, the current through an ohmic material is directly proportional to the potential difference. So that was the first equation you saw on the previous slide. Now, this is a graph that represents that same thing. Here we have the current on one axis, and we have the potential difference on the other. And we see that if the current is directly proportional to the potential difference, then we get a straight line here. And the resistance is the slope, or the resistance is 1 over the slope of this line here. So other materials and devices that we call non-ohmic are materials through which the current through the device is not directly proportional to the potential difference. Things that are non-ohmic devices include things like batteries and capacitors. Now, resistance is a function of the material the electrons in our current are flowing through. So we have an equation that we can use to find the resistance of a material. And so the resistance is equal to this quantity here, which we call the resistivity of our material, times the length of that material divided by its cross-sectional area. Okay, so here we have some very good conductor, let's say, and it's going to have a resistivity, which is a property of that material. The resistivity has units of ohms times meter, and this resistivity is something that we would have to look up in a chart here. And so I have a chart here of a bunch of different resistivities for a bunch of different metals, things that are good conductors. And so here we're representing this, this conductor, this thing that is a resistor, as sort of like a cylinder where it has some cross-sectional area here and some length. Okay, and so if we look at these conductors here, we see that silver actually has a pretty low resistivity. As we go down here, the resistivity of this material is increasing. So as you go to larger resistivities, that means you're starting to become more and more of a better insulator. So good resistors have low resistivities. Good insulators have high resistivities. And this is table 20.1 in your textbook. You can also refer to this, and you will be needing to refer to this for your homework. Now, over a limited temperature range, the resistivity of most metals increases linearly with increasing temperature. So that means that the resistance also changes with temperature. So here's an equation which shows how the resistivity changes with an increase in temperature. And here's an equation which shows how the resistance changes with an increase in temperature. Okay, so rho here is representing our resistivity. The sub O here, or sub-zero, that represents our resistivity here, or our resistance here, at some reference temperature. Often this reference temperature is going to be 20 degrees Celsius. The same thing with the temperature here. The temperature is our reference or baseline temperature, T sub O or T sub-zero here. And alpha is called the temperature coefficient of resistivity, and it has a unit of an inverse Celsius. And let's see, so the temperature is here. That would be some final temperature at which the resistor has been warmed to. And the rho here, or the R, that represents the resistivity or the resistance at some higher temperature. Okay, now this chart that I've put in here shows the resistance of a sample of mercury. So mercury here has a 0 resistance, that's on the vertical axis here, at very low temperatures, which is a property of a superconductor. So at low temperatures, mercury behaves like a superconductor. It has no resistance. But above some critical temperature, which is different for each material, its resistance makes a sudden jump and then starts to increase nearly linearly with temperature above this. So at very low temperatures, there are many materials that behave as if they have no resistance, but as they warm up, they start to have a resistance that behaves more linearly. Okay, so we're going to do 2 problems here together to practice using, thinking about resistance and using Ohm's law, and thinking about how resistance and resistivity can change with temperature. So here's the first problem. I'm asking you to calculate the resistance per unit length of a nichrome wire with a radius of 0.321 millimeters. And here's an example of what nichrome wire looks like. Now for part B, if a potential difference of 10 volts is maintained across a 1 meter length of the nichrome wire, what is the current in that wire? And if the wire is melted down and recast with twice its original length, find the new resistance, R sub n, as a multiple of the old resistance, R sub O. So our first part, we're asked to calculate the resistance per unit length, so R over L, of a nichrome wire with a radius of 0.321 millimeters. So if you've never heard of nichrome, nichrome is a nickel chromium alloy, and this is a wire commonly used in heating elements. So we can solve this problem by using our equation for resistivity, the equation for resistance, the equation that depends on the resistivity of our material times the length of the material divided by its cross-sectional area. So if we're looking for the resistance per unit length, we need to solve this equation for R over L. And so if I do that, I divide both sides by L, I have that the resistance over the length is equal to the resistivity times its cross-sectional area. Now, the resistivity is a property of a material that you'd have to look up in a table, and so the resistivity of nichrome is 150 times 10 to the minus 8 ohm meters. Ohm times meter, that's the units of resistivity. Okay, and I'm going to divide it by the cross-sectional area of a wire. So if you think about a wire, it's long, and its cross-section we can approximate as a circle. So the area of a circle is pi times radius squared, pi r squared. In this case, r is the radius here. So we've got pi times our radius, 0.321 times 10 to the minus 3 meters squared. All right, so just plug those into our handy calculator and we'll find that the resistance per unit length of this nichrome wire is 4.6 ohm over meter, ohms per meter. Okay, so where does that unit come from? So if I look here at the units on my answer here, resistance per length, I've got an ohm times meter on the top, and I'm dividing it by a unit of meters squared. So we've got 1 meter on top, meter squared on the bottom, and one of those meters cancels out, and so we're left with ohm per meter for my unit. Okay, so that's part A. For part B of this problem, suppose I have a potential difference of 10 volts maintained across a 1 meter length of nichrome wire. L is 1 meter. What is the current in this wire? I. So in order to solve this problem, we can use our handy equation for Ohm's law. Ohm's law says that our potential difference is equal to the current times the resistance. So I solve this equation for the current. Current is equal to V over the resistance. We already know what our potential difference is right here, 10 volts. We just need to get our resistance. And we found the resistance per unit length in the previous part of this problem, 4.6 ohms per meter. So my resistance is just going to be my resistance per length times the length of the wire that I'm given for this problem. So I'm just going to take 4.6 ohm per meter and multiply that by the 1 meter length of wire that I'm given. And so that just simply shows us that the resistance of this 1 meter length of wire is going to be 4.6 ohms. So our current that we're looking for here is just going to be 10 volts divided by 4.6 ohms, and that equals 2.17 amperes. Now suppose that our nichrome wire is melted down and recast with twice its original length. We need to find the new resistance, which I'm going to call R sub n, as a multiple of the old resistance, the previous resistance it had, which I'm going to call RO. So Rn is our new resistance, RO was our old resistance or our original resistance. So the thing about this problem, just the way to think about it, is we have the same volume of our wire both before and after it's been recast or changed its shape. So we know then that the volume of our new wire has to be the same as the volume of our old wire. Now if we think about a wire, I'm going to just draw it like this, it kind of looks like a cylinder. It has some length L and it's got some cross-sectional area A. And so the volume of this wire or this cylinder is going to be the cross-sectional radius here A times the length of the wire that I'm using. So we can replace the volume here with the new cross-sectional area times the new length, and that has to equal the original cross-sectional area times the original length. Now we know that the new length is twice that of our old length or our original. So new length is equal to 2 times the old one. So if I solve this equation that we just wrote down here for the new area, AN is equal to the original cross-sectional area times the original length divided by the new length. I know that the new length is twice the old length, and so our new cross-sectional area This is the same thing as the old cross-sectional area times the old length divided by 2 times the old length. And we see that L0 or LO cancels on top and bottom, and so we're left with the fact that our new cross-sectional area is equal to the old cross-sectional area divided by 2, half of the old cross-sectional area. And that makes sense if we think about the fact that if we're changing the shape of this to be twice as long as the original shape, but keeping the same volume, if we have to stretch it out, we have to shrink the cross-sectional area. And so this new cross-sectional area is smaller than our old one. So that makes sense here. Okay, so now we're looking for the new resistance in terms of the old resistance. So if we look at their equation for resistance, that equals our resistivity of the material, which does not change, times the new length divided by the new cross-sectional area. So remember that our new length was twice the old length, and we're dividing it by our new area, and our new area was half of the old area. So this is going to equal to our old area divided by 2, okay? So when we divide by a fraction, it's the same thing as multiplying by the reciprocal. So this is going to equal our resistivity times 2LO times 2 over our original area, okay? And so if we look at our equation for resistivity, resistivity is equal to if we look at our equation for resistance, resistance is equal to our resistivity times the length divided by the area. So here we've got a resistivity, we've got a length, and we've got an area. Okay, so all of those terms there, those equal to our original resistivity. And then we're left with 2 times 2. So our new resistance is going to be equal to 2 times 2, or 4 times our old resistance, or our original resistance, okay? So that's what we're looking for. We've taken our wire, reformed it so that we made it twice as long as it originally was, and when we make it twice as long, we don't change the resistance by a factor of 2. We actually increase the resistance by a factor of 4. Here, we're going to apply the temperature dependence of resistance. So a resistance thermometer, that's what this thing is right here, measures temperatures by measuring the change in resistance of a conductor. And this particular one is made of platinum, and it has a resistance of 50 ohms at our reference temperature of 20 degrees Celsius. Now, when this device is immersed in a vessel containing melting indium, this is an example of what indium looks like, its resistance increases to 76.8 ohms. From this information, find the melting point of indium. This problem has the goal of applying the temperature dependence of resistance. And we're going to use a device called a resistance thermometer. So a resistance thermometer measures temperature by measuring the change in resistance of a conductor, change in resistance of a conductor as temperature changes. A particular resistance thermometer has a resistance of 50 ohms at a temperature of 20 degrees Celsius. Now this device is going to be immersed in a vessel containing melting indium. And when it's immersed in this melting indium, its resistance is increased to 76.8 ohms. And we're asked to find the melting point of indium, which I'm going to call T final. And so since our resistance thermometer is immersed inside this melting indium, it also achieves a final temperature that's the same as the temperature of the melting indium in which it's immersed, okay? So if you've never heard of indium, it's an element on the periodic table, and it's the softest metal that is not an alkali metal. Now, we have an equation which relates the resistance of a material to its change in temperature. So we have the equation that the resistance, the final resistance of a material, is equal to its resistance at some reference temperature times, oops, it's not a times, times 1 plus alpha times T minus T0. Okay, so in this equation, R, that's our final resistance that we've achieved here. R0, that's our resistance at some reference temperature T0. T0 is our reference temperature here, which in this case would be 20 degrees Celsius. Alpha is what we call the temperature coefficient of resistivity for a material, which you'd have to look up. And T here, that's the final temperature that we're looking for. In this case, that's the final temperature that our resistance thermometer achieves, which is the same as the temperature of the melting iridium, which is what, or sorry, the melting indium, which is what we're trying to solve for here, okay? So we need to solve this equation here for T, for temperature. And so the first thing I'm going to do is divide both sides by R0. So R over R0 is equal to 1 plus alpha times T minus T0. Okay, and then I subtract 1 from the right-hand side, so then I have R over R0 minus 1 is equal to alpha times T minus T0. Okay, so I'm going to do a little trick in order to combine this fraction with this minus 1 here. So 1, this 1 right here, we want to get common denominators here. So this 1 we can write as R0 over R0. That's the same thing as 1. And so this expression that we have right here, R over R0 minus R0 over R0, we can rewrite that as R minus R0 all over R0. And that equals alpha, our temperature coefficient of resistivity, times T minus T0. Okay, so now I'm running out of room here. I'm going to take this equation over here, and now I'm going to divide both sides by alpha. So then I have R minus R0 over alpha times R0 equals T minus T0. Okay, and then I have one more thing to do. I just have to add T0 to the other side. So then we have T equals R minus R0 over alpha times R0 plus T0. Okay, so this will give us our melting point of iridium, or sorry, indium. Keep on saying iridium. And that is equal to our final resistance, which was 76.8 ohms, minus the original resistance of our resistance thermometer, which was 50 ohms. And I'm going to divide that by our temperature coefficient of resistivity. And for indium, that value is 3.92 times 10 to the minus 3, and it has units of inverse temperature, so it has units of inverse degrees Celsius, and then we're going to multiply that by our initial or our reference resistance, which is 50 ohms, and then add that to our reference temperature, okay, which is 20 degrees Celsius, okay? So plugging all those values in, we get that our final temperature, the melting point of indium, is 157 degrees Celsius. So we've approached near the end of our mini lecture about resistance, and I wanted to put this quote behind me, which appears to be chopped off a little bit, but resistance is futile. And behind me here is a resistor that has literally burned up on itself. So this resistor has severely overheated, if you couldn't tell. When a resistor is placed under a voltage that approaches the upper limit of its power rating, the resistor generates more heat than normal, and this is an example of that. Now, myself, when I was an undergrad, I had a laptop that got so hot, all the internal devices and the resistors in there got so hot that the motherboard inside my computer actually melted. So this is something that can happen to you in real life. And also, if your phone gets too hot, a similar thing.